A lot of times they don't worry about units, but if you're calculating a slope and you're coming up with like a new number that they didn't give you, I would definitely make sure there were units on there. So, because that might very well be one of the points, might be having the correct units. I don't know if it was. Yep, for correct units and no more than 4 significant figures on your value of A, you got a point for that. So make sure you have the right units. All right, so getting to the point of what we were doing for this problem was we had to figure out the work done by the cart in compressing the spring point 1 meter from its equilibrium length. So we're going to go back with work equals, I got the wrong marker, the integral of f dot dr. If we're compressing the spring, we're assuming that we are putting in a force that's equal to the spring force. So this is going to just be equivalent to Fs. Alrighty, so can we pull f out of this integral? Well, first of all, let's get rid of the dot product and replace it with our cosine theta. But if the cart's doing some work in compressing that spring, it's going to put a force on the spring in the same direction the spring's being compressed. So what's our theta? 0, so we don't need to worry about this. And again, we're saying the force that the cart has to do is somehow, equivalent to the force of the spring here overall. Blah, 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 blah. All right, so Fs, what are we going to sub in for that?
X squared.
1700 x squared.
Okay, we're going to plug that in. Why couldn't we pull it out of the integral? It changes with x. It's not a constant force, so we're going to...
Could you pull out the 1700 though?
Yes, you can. So we're going to have 1700 x squared dr. Again, do we care about the fact that this is x and we have r? No. Again, why? I don't know. Maybe on this new sheet they'll go back to x's. Because again, they're always giving things in terms of x. So I never get it. But that's really a dx. So you can pull out the 1700 because it is a constant. X squared dx. And what are we going to integrate? What are our limits going to be? 0 to 0.1. Do the calculus. The integral of x squared is just x cubed over 3. Plug in your 0 to 0.1. When you plug it in, what do you get as your answer?
I don't want to do
0.563, but I use 1688 instead of 17.
All right, so you're going to all be close. So it's around 0.57. 0.57 joules was the work that was done to compress the spring. All right. So again, we have more problems. You can work on them. Any of these, you can get the answers right off of AP Central if you want to try them. They all have, again, a general work theme to them, or work is at least a part of one of the questions. It's very rare, again, on the AP exam to find one question that's devoted specifically to one topic. So, this question was their experimental question. So you had the data analysis, then you had work, then you're going to have conservation of energy. If you look on the one on the front page, there's going to be kinematics, there's going to be, kinetic energy, there's going to be work, it's going to be a bunch of different stuff, and so on. All right.
So what's the answer for F?
The F answer, if you had done it, and again, we can come back to it when we get to conservation of energy, which will be the last thing we do today. But the F answer was about 1.5 meters per second.
Okay.
So, all right. So moving on to another idea. Always good to move on. So far we spent the whole morning looking at work and its relationship to one kind of energy, and that energy was? Kinetic energy. There is another energy that exists, or some people like to argue that it's not really energy, but we're going to count it as energy, but it doesn't matter. But there is another type of energy, and that is what kind of energy? Potential energy. So we looked at kinetic energy. Now we're going to look at potential. I'm going to spend from now until lunch, probably talking about potential energy.